All right, so I'm going to include the warm-up here on this recording because it's a pretty good warm-up. It says to find the limit as x goes to positive infinity or negative infinity for this function 3 to the x. So in this case, we are analyzing what part of the graph when we go to infinity or negative infinity. What do we call it? The end behavior. Good. We're looking for the end behavior of the graph. What are the y values doing on the left end and the right end of the graph? What if we were to zoom into outer space on this function, what would we see? Okay? So if you're not sure what 3 to the x graph looks like, and you will by the end of this semester, I guarantee, but for now you could just kind of plug in. So 3 to the infinity. Infinity is not a number, but what that means is it's 3 to the huge, 3 to the huger, huger. So if you want to kind of look at the sequence, it would be like 3 to the first, 3 to the 10th, 3 to the 100th, 3 to the 1000th, so on and so forth, right? That's what's happening. What is then happening with those numbers? They're getting really, really huge, like really, really fast. Like, gosh, if your money was growing like that, my goodness, you would be like Ted Turner, right? Very wealthy. So this is going to what? The magnitudes are going to positive infinity, right? So when we do this, this is our sequence, and the arrow means approaching infinity. But that's not how we write our answer now. We write our answer like this up here. We either say the limit equals infinity, we do it like that, or you, without putting the equal sign, you can write it directly underneath there, remember, and that's evaluating the expression. All right, so what would be another answer that would be acceptable on a free response other than infinity? My goodness, D and E, right. Sorry, I gave it away. On a free response, you could say D and E here and get credit. Remember, infinity tells you that the y values don't exist as a limit because they increase without bound. So it gives you more information. So that would be the multiple choice answer, infinity. As you go out to the left, let's do the same thing. Plug in 3 to the negative infinity and look to see what that's doing. Well, we have a negative exponent. We don't really think that well in terms of negative exponents. So what could I do to get rid of it? Bring it to the bottom. So that becomes 1 over 3 to the positive infinity. And now all of a sudden those ratios are going to be like 1 over 3 to the first, 1 over 3 to the 10th, 1 over 3 to the 100th, so on and so forth. What are those values approaching? Those are approaching 0. The magnitude is getting smaller and smaller and smaller because the denominator is growing faster than the numerator, which is not even growing. So this is going to equal 0 like that, or you put 0 directly underneath it. Now, based upon our definition of the end behavior asymptote, do we have an end behavior asymptote on this function? Based upon this analysis, we got infinity on one side and 0 on the other. 0 is a what? What do we call it? Horizontal asymptote. So now down here we'll say F has a horizontal asymptote, which we can abbreviate HA, at x equals or y equals? Y equals 0. Okay? So remember, that is the definition of a horizontal asymptote. If either one of those two end behavior analysis values is an actual constant, a finite value, like 0, you're going to have a horizontal asymptote at y equals. So notice there is a horizontal asymptote, but it doesn't affect the graph on the right-hand side. It only affects the graph on the left-hand side. That's fine. Okay? Here's what the graph looks like. Some of y'all might actually know this belongs in the family of functions that are not polynomials. What are they if the variable is in the exponent? They're not polynomials. They're called? No. If the variable's in the exponent, they're called exponential functions. We are going to study exponential functions in an entire chapter later on, okay? So this is an exponential function. Here's what it looks like. It has a horizontal asymptote on the x-axis, right? Y equals 0, but it looks like this. It only affects the graph on the right-hand side. Passes at 0.01. So this could be the graph of 3 to the x power. Now, when you study exponential functions in like a science class or biology class, you're usually dealing with first quadrant problems, right? You usually have time in years on the x-axis, and then on the y-axis, you're measuring like the number of, bacteria, okay? And so you start with the seeding value. You start with 1 bacteria, and it's kind of like maybe like mitosis. That would be 2 to the x, right? 1 cell splits, becomes 2. Those 2 split, it becomes 4. 4 becomes 8. 8 becomes 16. 16 becomes 32. So the more things you have reproducing, the faster it grows. So this is called exponential growth. All right? So we start with a single value, and then this one triples. Bless you. This one triples every cycle. Okay? So we're going to study those later on. You can see here clearly that there is a horizontal asymptote, but it only affects the graph on the left. All right. Any questions or comments on the warm-up? Y'all warm? Nice and warm? All right, so let's review what we did on, oh gosh, it was Thursday. When we're finding end behavior of rational functions, and remember a rational function is nothing more than the ratio of two polynomials. Polynomials being like really nice positive exponents, integer values, 1, 2, 3, x squared, x to the cube, whatever. No negative exponents, no fractional exponents. We can analyze the end behavior just by comparing how fast the numerator and denominator grow with respect to each other. So the first case was, if the top grows faster than the bottom, and I gave you an example here, right, then our magnitudes are getting really big. Could be really big magnitude to infinity or negative infinity. All right, so that would be like x cubed over x squared. X cubed grows faster for large x. X to the 10th over x to the 4th. X to the 10th goes faster. Those would go to infinity or negative infinity. Case 2 was if we flip that. If the bottom grows faster now, like we just saw with 1 over 3 to the infinity, then the ratios are getting smaller and smaller, and they're approaching 0 each and every time. And so in that case, we said there would be a horizontal asymptote at y equals 0 every single time. So the example would be like x cubed over x to the 4th. X to the 4th goes faster. X squared over x to the 5th. Doesn't matter the degree difference. As long as the bottom goes faster, it's going to go to 0. And then case 3 was if they grow at the same rate, like x cubed over x cubed, x to the 4th over x to the 4th. So in general, if it's ax to the n over x to the n, the limit is going to be, or I'm sorry, ax to the n over bx to the n, it's going to be a over b. That's the limit. So you will have a horizontal asymptote at leading coefficient over leading coefficient. All right, so those are the three cases. Now we get to try them out on D, E, and F. So let's review what the instructions are asking us to do. They are asking us to evaluate A, the limit as x goes to negative infinity of f. B, the limit as x goes to positive infinity of f. And then part C, it was asking us to make some kind of claim about horizontal asymptotes. So I'll do this one with you. All right, now because we're looking for end behavior only on a ratio, we only need to look at the leading terms in the top and bottom. So what makes a lead dog in a pack of dogs? He's usually the one in front. Like on a sled, pulling the sled, the lead dog is in front. But is that what makes a leading term a leading term? Is it always the one in front? No. The leading term is always the one that has the largest exponent. So in this case, it turns out that 3x is the larger exponent because 1 is a constant. So you can forget about that. And in the bottom, 5x squared is in the front, and he is also the leading term. So remember, you can obliterate everything else with the leading terms only in this case because we're looking at the end behavior. All that stuff that I just crossed out will definitely affect the graph locally. But we're zooming out. We just look at the end behavior. And now we compare. Which one grows faster, x to the first or x to the second? X to the second. So for large values of x, the bottom grows faster, which means the ratios are approaching what? 0. From both sides, it's going to approach 0. Okay, now 0 is a very interesting number because 0 is known as the x-axis. Y equals 0 is known as the x-axis. So it's the dividing line between positive numbers and negative numbers. So here's something else we could do to kind of help us moving down the road. I want to know now, is it approaching 0 from above the x-axis or below the x-axis? That's going to be pretty easy to determine because values above the x-axis are positive and values below the x-axis are negative. So let's go ahead and see. Here's how you could determine if it's approaching 0 from above or below. Once you know it's 0, just write that down. But now notice on part A, we're going to negative infinity. So as we go to the left, all of our x values are negative. Just plug a negative into the leading terms and see what sign you get. In the top, negative to the first is negative. Negative times 3 is negative. So my numerators are going to be negative. I write that right here. In the bottom, what's negative squared? Positive times positive 5 is positive. So as I go out to the left, my ratios are always going to be negative over positive, which is what type of number? Negative. And so because negative numbers are found below the x-axis, we know that the limit is 0, and we're approaching it from where? Above or below the x-axis? from below. Okay? Just a little bit of extra information that we kind of get for free. And we'll do the same thing for the right-hand behavior. We still know we're approaching the x-axis, but for positive x values, when I plug it in, 3 positive to the first is positive, and 5 positive squared is positive. So we're getting positive numbers, so we're approaching 0 from above. I should say above the x-axis, just to make it a little more clear. There we go. From above the x-axis. We will be sketching these guys later on, and that's going to be helpful information. Okay, so there's that. Based upon A and B then, can we say anything about the existence or non-existence of a horizontal asymptote? Yes. We'll say F has a HA at y equals 0. So you write in a complete sentence. F, you could use F instead of f of x. Remember, the name of the function is F. You could also put f of x if you like. F has a horizontal asymptote at y equals 0. Not just 0, not x equals 0, but y equals 0. Okay, sweet. Any questions on that one? All right, letter B, I'm going to let you do it, but I'm going to get you set up with the notation first, which was the following. We focus on the notation first. Some people are coming along nicely with that. Some people are still struggling. Make sure when you write the limit, like I just did, that you always have a function behind it, between that and the answer. Because if you just put the limit equals, let's say the limit equals 7. I'm just making something up. This is going to be wrong because there's no function there. And remember, the limit are the roads. And when you put a function there, you're defining whose graph we're using as the roads. And if you don't put either the actual expression or f of x in there, we don't know what road we're traveling on. So make sure you have an f of x there. Here's another thing that I see students do. They put an equal sign between the limit and f of x. That's the wrong place to do it because now you don't have an f of x behind the limit. You're saying the limit is f of x. That's not. So we have the limit of f of x, if you want to read it like that first, is, as x goes to negative infinity, what? So that's part A. Part B, very similar here, the limit x goes to the right of f. And then part C, we'll do the horizontal asymptote analysis. So go ahead then, if you've gotten the 3 things written down, you focus on your notation first, then go up to the function and do your analysis. Analyze how fast the top grows with respect to the bottom. One of 3 cases. That if it were 3 over 3, you could just put 1. Yeah, but is it 3 over 3? Is that the leading term? Well, first of all, if it were 3x to the first over 3x squared, then x squared would be bigger than 1, so they would go to 0, not 1. Right, but that's not the leading term. There you go. Remember, the leading term is not necessarily the one in front. And I can jumble the terms around by the associative property of addition. And will I do that? Heck yeah, I'll do that. Yeah. Well, you got it identified. What are they? Are they growing at the same rate? X squared. X. Well, yeah. You just look at the degrees. The 4 and the 3 are no big deal. So if you were just to look at that, those would kind of divide out, right? X squared would divide, and you'd be left with 4/3. Yeah. Okay. Yeah. In the top, the leading term, is it 3x? No. The leading term is positive 4x squared. He's leading from the rear. That's a different type of leadership style. So he's on the back, so it's the 3x minus 2 that we can ignore. And on the bottom, the positive 3x squared is the leading term because it's the largest exponent. He also happens to be in the front. So that's your first step, is analyzing the function and find those leading terms. Now we could say, and here's kind of something you could do. You could put a squiggle there, which means what? Not equivalent, approximately. That's your approximate symbol. That function then is approximately growing like a 4x squared over a 3x squared, and that's for large values of x. So you could say for large x. If we were to zoom out on the function f of x, we would not see all of its glorious local behavior like holes jumps, x-intercepts, local maximums. We would only see the behavior of 4x squared over 3x squared, which if you were then to simplify that, what would you do with your x squared? Divide them out, and you'd be left with 4/3. So what we're saying is, for large values of x, this function begins to look more and more like y equals 4/3. What does the graph of a constant look like? It's a horizontal line, yeah. So all of this right here would be the local behavior that this function would have, but as we zoom into outer space, we would not see it. There might be like there might be a vertical asymptote, there might be a hole, there might be a jump, something like that. We're zooming so far out, it just becomes lines, and all we see is this horizontal line. And so that's the answer. It's 4/3 on both sides. When the degrees are the same, you're always going to have a limit on each side of leading coefficient over leading coefficient, which means on part C, f has a horizontal asymptote at y equals 4/3. Now, we're not going to find out if it approaches 4/3 from above 4/3 or below 4/3, because 4/3 is an actual number. We have to actually compute numbers instead of just looking for positive and negative. So later on when we sketch this, there will be other information that will help us determine if the graph is approaching it from above or below. But right now, we'll just leave it as that. All right, so that would be case 2, leading coefficient over leading coefficient. Now on part F, go ahead and do it entirely on your own, including the limit notation setup. Leading term is not always first. Which one grows faster, the top or the bottom? Refer to the 3 cases in your notes up above. All right. A lot of y'all are getting the right idea. All right, if you're stuck, let me help you. In the top, the leading term is 4x to the 5th, because 5 is the largest exponent. So because it's end behavior, you can forget about all that. Here's where you want to be careful. In the bottom, the leading term is not 7. It's negative 6x to the 4th. If you get in the habit of like obliterating everything for end behavior analysis, that's fine. Just be careful when you obliterate like a 7 that you don't take out the what with it? The negative. That could be collateral damage. And if it's leading coefficient over leading coefficient, I guarantee you an answer choice on the test is going to have the same number with a positive or negative there. So you'd have the right idea, but you would miss it because you got the wrong sign. So it's negative 6x to the 4th. Now, if you want, you could put the squiggles here, not an equal sign. You could put a squiggles. That means that this function is going to look like 4x to the 5th over negative x to the 4th for large values of x. Okay? Which means that which grows faster, the top or bottom? The top. So anytime the top grows faster than the bottom, anytime, you know that your y values are going to get infinitely large in magnitude. So we know the answer for both of these is going to be some type of infinity. But I don't know yet what the sign of infinity is. I don't know if they're going to go to positive infinity or negative infinity. But I do know because the top's bigger in degree, it's going to be some type of infinity. So how could I come back and find the sign? Plug it in. Yeah, just like what we did over here on part A when we were determining if it was a positive or negative approach to the x-axis. You could do the same thing here. Just make sure you're plugging into the leading terms only. So let's go ahead and do this one. If we go out to the left to negative infinity, plug in a negative number to your leading terms. Negative to the fifth would be negative, right? Times positive 4 makes it a negative in the numerator. And then if you plug a negative into the bottom, negative to the fourth is positive. But now times negative 6 makes it negative. So what's a negative divided by a negative? It's a positive. So this is going to be positive infinity as you go out to the left. Now, of course, you don't even have to put the plus sign in front, because if it's not there, it's implied that it's positive 1. But you could put it there for emphasis. That's fine. And then we do the same thing for the right. We're going to positive infinity, plug in a positive x. Positive to the fifth is positive, times 4 is positive. And then the bottom, positive to the fourth is positive, times negative 6 is negative. What's a positive divided by a negative? A negative. So as we go out to the right, we're going to negative infinity. So you know it's infinity. You can come back and get the sign that way. Or you could do it this way. This is called the end behavior model. End behavior model, which I will abbreviate because that's a lot of words, EBM. So remember on the previous one I said that if you look at the approximation and simplify, you get 4/3. So when you zoom into outer space, you don't see the local behavior. You only see the line y equals 4/3. Question or stretching? Okay.
The B part.
Yeah.
Is that always, I've been reading that as always the X approaches general limit.
Yeah, these are all one-sided limits because you can't approach infinity from the right-hand side. So the end behavior limits by definition are one-sided limits. Yeah. So as x gets really, really big in the positive direction, or x gets really, really small in the negative direction. Okay. So we don't have to check the other side. We can't. We could do the same thing as we did over there. If we say it approximately is the leading term over the leading term, what happens when you simplify this little leading term over leading term? What is 4 negative 6 simplified to? 2 over negative 3, or just negative 2/3, right? The ratio is negative. And what's x to the fifth divided by x to the fourth? X to the first, which you can put off to the side. Instead of calling it negative, or I guess when you simplify, you would call it 2x over negative 3. That's the same as negative 2/3 x. Okay? If you then put a y equals in front of there, you have now created your end behavior model. So just like over here, y equals 4/3 graphs as a horizontal line. What does y equals negative 2/3 x graph as? Not a horizontal line, but a pitched line or a slanted line with a slope of negative 2/3. So I don't know what the y-intercept is, but I know a line with a negative slope is going to look something like that, correct? It's going to look something like that. And when we zoom out, we lose all the local behavior, right? Where there could have been, asymptotes, whatever, x-intercepts. We lose all that. We don't see it. We just see the end of the graph. And so this is why we call it the end behavior model. It has the exact same end behavior as the original function. So now you can answer the question a little bit faster. What happens to f as we go out to the left? Well, look at the end behavior model. As you go out to the left, it's going where? Up to infinity. And what is f doing as we go out to the right? Well, look at the line, y equals negative 2/3 x. It's going down to negative infinity, which is the answer. So it's almost a faster way to get the correct sign of infinity. So you have two ways to do that. You can either realize the top's bigger, it's some type of infinity, and then plug in to get the sign, or just simplify the leading terms and sketch the end behavior model and see what it does, okay? Now, in terms of horizontal asymptote, does this function f have a horizontal asymptote? No, okay? Because the answer to the two questions above, neither one of them is finite. They're both infinite. So there's no horizontal asymptote. But let's plant the seed here. There is an asymptote. Remember I said that we don't see the local behavior, but what this means then is the graph, as it goes to the left, it's going to go to infinity, and it's going to approach that line. That equation of the local behavior function is actually an asymptote. It's an asymptote. And guess what type of asymptote we call it? Diagonal would be good. Linear would be good. Those are all great names. We call it a slant or an oblique asymptote. But they imply the same thing. It's not a horizontal line. but it's a slanted or oblique or whatever y'all called it, diagonal asymptote. And the graph could do this, okay? So as it goes to infinity, on the left, it's using the line y equals negative 2/3 x as a highway to heaven, or as a, let's do classic rock analogy, as a stairway to heaven. Maybe it's going slower. The new version, I guess, would be escalator or elevator to heaven. I was writing stairway to escalator. That doesn't work. So as it goes out to the left, it's going to get closer and closer and closer to that line. And as you go out to the right, it's going to get closer and closer to that line, using that line as the highway to hell, the AC/DC reference. Okay? So you got Led Zeppelin and AC/DC on here. Now, you don't have to find the equation of the slant asymptote. There could be a y-intercept plus b. We'll save that for a later day. But right now, I want you to be able to figure out what type of infinity it is. Here's another little thing to think about. If the degree difference had been 2, if that had been x to the 6th over x to the 4th, then what is the degree difference? X to the 6th over x to the 4th would be x squared. Guess what type of asymptote we would have? A parabolic asymptote. Absolutely. So you can have asymptotes that are degree 1, 2, 3, 4, whatever. Okay? When it's degree 1, when the top is 1 bigger, it's going to be a slanted line. So 2 ways to figure out what type of infinity it is. Got it? So there's your 3 cases. All right? If the bottom grows faster, it's always what? Going to what? For large x, 0. If they're growing at the same rate, it's always leading coefficient over leading coefficient. And if the top grows faster, it's always some type of infinity. And we have 2 ways to determine the signs. Plug in or look at the end behavior model. All right, putting it all together. This is you. This is your check for understanding. It's easy for me to give you a graph and you pull the values off, but can you do this? If I give you these requirements to create the graph of a function, can you do it? I think you can. I'm going to give you a couple minutes to sketch the graph of a function f of x that passes the vertical line test from -5 to infinity that has these characteristics, at least. It can have more than that. If you want to add some extra requirements, it's up to you. But sketch a function that has these characteristics. This makes a fantastic free response question because answers should vary. Your function could be different than your neighbor's. 2 minutes, 2 minutes. You're trying this at home too if you're watching the video. 2 minutes. Yeah. Hint, start by drawing an x and y axis. And then look at the x values that we're talking about. You have to kind of make that graph have that behavior. There's also one like this in the worksheet. When you're done, make sure it passes the vertical line test. 1 more minute. All right, so here I'm going to go ahead and walk through. Keep going if you think you have it. The first thing I'm noticing is it says up here that the function lives from -5 inclusive and then all the way to the right. So -5, the graph does not live to the left of -5. So when I come over here, I'm just going to go ahead and mark this arbitrarily. 1, 2, 3, 4, 5. I'll call that -5. Okay. Now, I don't know what's going on at -5, but I know that the function lives there and not to the left. So now I start with this first piece of information. This piece right here, if I analyze it, -3 is the value of x I'm interested in. It says, as I approach -3 from the what side? Left, my y values have to be approaching -2. So there's kind of a target, -3, -2. So let's come over here. Here's -3, and then -1, -2. I'll just do that. I know I need to end up at -3, -2. So I'm going to put an open circle there for now. How do you want to approach that? Do you want to approach it with a straight line from above, below, from the left? This is where you have free will, however you want to draw it. I'll draw mine coming in like this. I don't know. Okay? If you wanted to draw it coming in from the bottom, that's great. If you want to have it coming in sideways, it's entirely up to you. It's your graph. We just know that that has to be the case. All right, and now the next piece, if I look at it, it says f of -3 also equals -2. That's an ordered pair, isn't it? Okay, so now guess what I'm going to do with that open circle? I'm going to fill it in. So the limit from the left equals the function value. All right, so now I filled it in. Cool. And then the next piece says, hey, when you approach -3 from the right-hand side, your y values are going to infinity. Oh, what graphical feature is going to live there to force them to go up? A vertical asymptote. Good, at x equals -3. So let me come in here and I'll draw a vertical asymptote. You could draw it all the way through the dot if you want. It's not affecting the graph on the left-hand side. It doesn't have to. And now it's going to go to infinity. So, I don't know. I'll draw something like that. Now, if you don't want to draw it there, guess what? You could draw it anywhere you want. Now, notice I'm not drawing it too far to the right of -3. I'm drawing a little bit to the left and right just to give myself an idea of what it looks like. I'll put it right there. That looks good. I like that. I could change it later if I want. Okay, now I move to this next piece. F of 0 equals 0. That's easy. That's an ordered pair again. What do we call the point 0, 0? Origin. So I know it goes through the origin. So there's a solid dot. And then I look at the next piece that it equates to. That's also the general limit at 0. General limit means the limit from the left and right are the same, and they both equal the function value. So those two right there tell us what about the function at 0? It's continuous. Good. At x equals 0. When the general limit, which implies the left and right being the same, equals the function value, the function is continuous. So you could draw, y'all said a line, that's fine. It could be a curvy line. You could have it go through the origin like that if you want. You could have it going through the origin like that if you want. Whatever you want to do. Because my graph is down there, you might want to just draw it kind of as if it were coming up and going through. And then you could connect those later. That would be fine. I'm going to go ahead and make it do that. Why not? It's my graph. I'm going to make it go through like that. Whatever you want. But notice just by drawing that little piece, I've met those requirements. It's continuous through 0. Okay, next one. Next line. Now the next value is 3. So as I approach 3 from the left, I'm going to 4. So 1, 2, 3. 1, 2, 3, 4. So there's my target. It's the open circle 3, 4. And I got to approach it from the left. So I'll just come in like that. I'll just have it approaching from underneath. Again, your choice. You can have it coming in sideways or from above, whatever you want. I'm going to come through and connect those lines later on. Right now I'm just trying to meet the requirements. If I approach the same x value 3 from the right-hand side now, I got to be approaching 1. So now my target is 3, 1, and I'll approach it from underneath. Why the heck not? Okay? My graph again. Approach it from above if you want. Right there, we know that there's a what at x equals 3, just based upon that. Yeah, f has a jump at x equals 3. And now the next piece says, hey, f of 3 is -1. That's the function value. F of 3 is -1. So let me move this label down. -1 is going to be right here. That's a solid dot. Does that affect the jump at all? No, because it's still a non-removable discontinuity. And now there's only one last piece. And it says, when I go out to the right, forever and ever and ever, I've got to be getting closer and closer to what? 2. So here's 2. What does that mean graphically lives at 2? There's a horizontal asymptote, good, at y equals 2. All right, so I'm going to go ahead. I'm going to draw that horizontal asymptote all the way through 2. It's only going to affect the graph on the right-hand side because the left-hand side is a starting point, -5. So now how am I going to make sure I do that? Well, I just have to be approaching. I can approach it from above or below, right? I'll just approach it from above. Why the heck not? Okay, so what I've drawn right now in purple meets the requirements, yes? And I've met all the requirements. And I had flexibility, too, in where I drew my pieces left and right. So now all I have to do is come through and finish the graph by connecting them somehow, making the function values exist somewhere, somehow, and it's my choice. So here's what I'll do. At -5, I'll just have it come up here, and I'll have it stop with an open circle. And because it says the function exists at -5, I'm just going to go ahead and put a solid dot down there on the x-axis. Might as well. All right, so now what am I going to do here? I'll go ahead and, you know what? I'm going to put another vertical asymptote at -1. It's my graph. It's my choice. I can certainly add extra things. So now I'll make this one go down to -infinity, and I'll make this one go up to +infinity. The purple stuff was required. The green stuff now is just me being creative. So if you don't want to do that, you don't have to. As long as you have a solid dot somewhere, that's fine, because it has to be defined everywhere on the interval. So if you just put an open circle somewhere like I did here, just put a dot somewhere else. That's fine. Yeah. Now, for me, from here, I'm just going to go ahead. I don't want to get too crazy here. I'll just connect those with a line. Might as well, right? Or you have quite a bit of opportunity to do a lot of other things there. You can add another jump. You can add a hole, whatever you want. In fact, I think I'm going to do that. Let's add a hole. I'm going to add a hole. I'm going to say it comes in here, and then there's an open circle, and then it goes like that. And then I'll just leave it defined right there. My choice. Okay, so now all I have to do from 3 is make sure it approaches infinity. I'm going to go ahead and have it come up and cross, and then I'll cross again, and then I'll cross one more time, and then I'll just connect it. And there it is. I'll label it now as F, and there's your graph. So the purple stuff is the required stuff. The green is just me connecting it however I want. One last check before I end. Is the function defined everywhere from -5? Do I have a dot or a piece of the graph everywhere? And does it pass the vertical line test? Yes. There's one point where I left it undefined. That's at -1. So let's go ahead and do something at -1. Let's just make it another x-intercept. So this would definitely be some kind of piecewise function, right? Now it passes the vertical line test, and every x value has a y value on that interval. Done. So these would be fun to grade for me because everybody's is different. I get to see how exciting your lives are inside your head when you come up with these crazy graphs, right? Answers will vary. All right, any comments or questions on that? Yeah. What's that? Sure. Absolutely. Yeah, it could be a straight diagonal line right through 0. Yeah, as long as it flows through 0. It could flow through, it could even flow through horizontally if you want. It could bounce there if you want, like a parabola. You can have it bouncing there. That's fine. However you want. It just has to flow through 0. Okay, let's review. Last little part here, example 12, summary of the whole section. If the limit from the left of some x value c, so c is just an arbitrary x value. It's not infinity. It's like 5 or -10. If the limit from the left equals the function value there, which equals the limit from the right, what can we say about f? Continuous. This is the road coming in. It equals the bridge in the middle, and it equals the road going out. We could say that f is continuous at x equals c. Okay, that's your 3-step definition of continuity. Road, bridge, road. All right. If I take the function value out of the mix, and I just compare the two limits, if the limit from the left equals the limit from the right, and they both equal L, where L is finite. That's kind of important. You might want to add that. If the limit from the left equals the limit from the right, the roads are lining up. What can we say about the general limit? Does it exist? Yes, and it also equals L. Okay? If the two one-sided limits are the same value, then the general limit exists. Some people get this confused with the continuity test, but this is not the continuity test. This is just the general limit. This is just looking at the roads. Notice there's no F of C analysis. If the road from the left is matching up to the road from the right, we say the general road exists, okay, essentially. All right, let me go ahead and write that underneath here. It exists. And vice versa, right? Okay, how about this? If the limit from the left of C does not equal the limit from the right of C, let's say that they both exist. One is equal to L1 and one is equal to L2. So they're not infinite, okay? They're coming into two different y values. Then what can we say about the function there? It's not continuous, and what type is it? F has a jump discontinuity at x equals c. Remember, it's a non-removable jump discontinuity. So it doesn't matter if the function value exists or not. If the two one-sided limits are coming into two different y values, F has a non-removable jump at x equals c. All right, how about this one? If the limit from the left does equal the limit from the right, let's say they both equal L, but that is not equal to the function value. Either the function value is equal to a different number, or the function value doesn't even exist. What can we say about F at x equals c? Good. F would have a hole, and we could say at the coordinate. What's the coordinate of the hole? Let's say that f of x is equal to L1 and f of c is equal to L2. There would be a hole at x equals c, comma what? Is the y value of the hole the limit value or the function value? No, not L3. It would be L1, right? It's the y value of the limit, because this is coming in like this is going out like that. There's L2, here's L1. Okay, the y value of the hole is the limit value. Okay, and then the last one here. If you're approaching an x value from the left, and your y values either go up or down, and or if you approach that x value from the right, and your y values go to infinity or negative infinity, what do we have on the graph at x equals c? What forces the y values to go up or down to infinity or negative infinity at a specific value of x and not at the end of the graph? A vertical asymptote, yeah, at x equals c. At x equals c. So that's the only asymptote that is a discontinuity. All right, and then the last piece here, if the limit as x goes to infinity equals L1, I'll say, add a little subscript. Or if you go out to the left, it goes to L2. L1 could equal L2. That's fine. Or they could be two different numbers. What can we say then about the function? L1 and L2 are both finite. F would have a what? Good. A horizontal asymptote at, we could say y equals L1 and y equals L2. A function can have at most two horizontal asymptotes because it's an end behavior asymptote and there are two ends to the graph. A lot of functions, though, that have them just have one horizontal asymptote, and that's fine. And they affect the graph the same way on both sides. But we also saw a graph this morning on the warm-up that had a horizontal asymptote, and it only affected the graph on one side. That was the exponential. So a function can have 0, 1, or 2 horizontal asymptotes. That's it. All right, any questions on this lesson? There's a lot of good stuff in here. We have like 12 minutes, 13 minutes for you to get ready for tomorrow's quiz. Let me show you on the worksheet. I know you've probably already started the worksheet because we've already tested over parts of 2.2. But what is kind of new? Well, if you look at your worksheet from 2.2, again, we're on 2.2, backtracking. Example 8 and 9, those are new ones that we didn't do on the last test. So those would be relevant for today. Let's see what else. On the on the free response, example 13 is really good. It's got part A, B, C, D, E, and F. I will say this on the key. If you check on the key, part I messed up. It says none. That's wrong. I need to fix it. There is a horizontal asymptote at y equals, and I'll let you figure it out. Should be at 0, okay? I just lied. I'll tell you. So sometimes the key is wrong. Someone pointed that out to me this morning. That's great. I'm human. If you go through and you discover an error, let me know. I'll fix it. It's also good for you to spot errors. When the teacher makes an error, because you know that there's cognitive dissonance, that's just the level of understanding that you're at. That's a good thing. So just let me know. No big deal. We'll fix it. All right? But those are all good. Some of those are ratios, some of those are not ratios. And I like piecewise functions. So I always like piecewise functions in continuity tests. Piecewise are my favorite. And then, of course, number 24 is kind of like what we just did on the last problem in the notes. Putting it all together, there's a different set of criteria. So this would be more like a free response question on a test, not really a quiz question. So you can pretty much guarantee tomorrow that I'm going to ask you for the limit as x goes to infinity of rational functions, and I might give you, you'll have 3 at least, right? Maybe one where the top grows faster, maybe one where the bottom grows faster, and maybe one where they grow at the same rate. So you can kind of start anticipating those types of questions. So that's it. Any questions on 2.2? Are we turning in the worksheet? No. Are you doing the worksheet? Yes. So retest is tomorrow morning at 8, but if you still have questions, you can still come in. We'll sit at the desk and we'll talk quietly while people are retesting. So tutorials are always open. Yeah.